So I will, so just recall, so h of px, so we know all this, but just px of a log px of a, d of px qx, a belonging to x, px of a log px of a divided by qx of a, plus infinity if support of p is inside support of q. So for every p of x that is positive, you have q of x that is also positive. Otherwise, if for some px of you have something positive, but q of x is zero, then the divergence is defined as infinity. Okay, so this is the I don't think I gave a statement of the Stein's lemma, but I essentially proved everything. So let me just go ahead and state it and identify all the elements. So Stein's lemma. Suppose px and qx are PMFs on x, then for any sequence of sets satisfying I should just have a given epsilon greater than 0 uh, if for any sequence an of set satisfying limit n tends to infinity p xn of xn is greater than equal to 1 minus epsilon, we have limit n tends to infinity 1 by n log q. Oh, sorry, I should have. We have limit n tends to infinity xn belongs to an minus is greater than or is greater than or equal to d of we have this is sorry less than or equal to d of px qx. Furthermore, there exists a sequence an star satisfying the above. Um, uh, Satisfying, I'll say, I didn't have to write it twice, but anyway. and equal to. So what I'm saying is that, given any epsilon, if I have a sequence of sets such that the probability of falling in my set an is large, then it can't be true that the probability of falling in that set from another distribution falls too rapidly. Okay, so really what this is saying, is that Qn of xn belongs to an. This can't really fall faster than this cannot fall faster than e power minus n times d of pq. It has to it can't fall faster than that. That's why when I take the minus n log, the number I get is not going to be greater than d of pxqx. If it is greater than d of pxqx, then that means that the probability is falling off too rapidly. So I should kind of say this. I mean, again, this is dot equal to, in the sense the exponents are equal. That's what it says. Yeah, so we did pretty much everything except for the last part, which is, showing that for any sequence that is true. And I pretty much went to the proof yesterday and didn't, I pretty much completed it, but I'll just do it. So suppose an is a sequence such that limit n tends to infinity, xn belongs to an, p xn of an, xn is greater than equal to 1 minus epsilon. Suppose this is true, then let b I think, okay, b I had yesterday. Okay, so let a tilde n equal to t delta n px intersected with an. Okay, so what am I looking at? I'm looking at qxn of xn. So xn belongs to an, right? So we'll make one observation. So we know xn belongs to a tilde n implies p xn of xn is at most exp minus n times h of px minus delta. It can't be it can't be small, it can't be larger than this. So that means so that means if I look at so the idea is that I should have gathered enough number of them. So let's do the following. So I know is at most this much. So consider. Oh, okay. So probability that a xn Pxn of xn. So this is less than equal to xn belongs to so how do I say this? So xn okay. So an intersect an minus a tilde n. So Pxn of xn plus xn belongs to a tilde n. So I'm separating out a tilde an into two parts. So this is the picture. So this is an, right? So this is T delta n, and this is A tilde n. Okay, so I know that so I know this, right? So this is this guy. So this guy, so this guy is here. Okay. So this I know is at most xn not belonging to T delta n, because I am going over. So not only those guys inside an, but I will go even further, no problem. And this is all those xn's belonging to A tilde n, Pxn of xn. So I know that the probability of falling outside the typical set is at most epsilon, right? I mean, for the large enough n. And here I have something like this: xn belongs to A tilde n. This is at most exp. This is the bound I wrote down before, h of px minus delta. This is the bound I wrote here. So that gives me, so I have, recall the left hand side is 1 minus epsilon. So this tells me that I'm going to just flip the term. So xn belongs to A tilde n, exp minus n times h of px minus delta. This is greater than 1 minus 2 epsilon. So which means that my size has to be at least 1 minus 2 epsilon times exp n h of px minus delta. Okay. So now I am in a position to look at, so now, so we have this. So I'll call this 1. And now we are looking at consider I want to go on the right. Okay, so xn belongs to a n. I want to show, okay, xn belongs to an q xn of xn, q xn of xn. This is what I'm looking at. This I know is greater than or equal to this thing. Xn belongs to A tilde n, because I have taken a smaller set. I've only looked at the intersection. So the probability of false alarm in a smaller set is going to be smaller, but this itself is sufficiently large. The reason is because I'm going to get so we are on an tilde, sorry, an tilde exp minus n times. So I'm going to be I'm going to, since you have seen this step so many times, I'm going to just go a little fast here. So so this is so there is a 1 plus delta by log cardinality of x. summation A Px of A log Qx of A. Okay. Yeah, this is right because no, so I have 1 by Qx of A because I will have something like this. So recall, so this is Qx of A n times Px of A. I mean with the deltas and all that ignore. So I'll have, so this will give me exp n times Px of A log Qx of A, which I'm writing with a negative at the bottom. So this is greater than or equal to, now the terms inside do not depend. So I have T delta n, sorry, A delta n, A tilde n exp minus n times 1 plus delta by log cardinality of x. A Px of A log 1 by Qx of A. Questions? So this is h of px. H of px has a negative outside, so that is why you get exp minus n times 1 plus delta by log cardinality of x. A Px of A log Px of A divided by Qx of A. So this gives you exp minus n times d of Px Qx. So this is a lower bound. Questions? So that gives me the Stein's lemma. Okay. So I will now questions, thoughts, remarks.
Sir,
Yeah.
here in the last, we replaced cardinality of A tilde n with the equation 1, right?
Yeah. 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 So there is a 1 minus 2 epsilon. If are you looking at that?
It is.
See, minus A Px of A log Px of A is h of this is h of Px. So here I have exp n times h of Px. So it's going to be minus Px of A log Px of A. And because I have the minus outside, it comes in the numerator. Is that okay?
Okay, sir.
Yeah. Okay, so that means we have got both sides of the, we've got both upper and lower bounds. So this is your theorem in, I don't know what, yeah, I think this is theorem 1 in chapter 1 of Chisar and Corner. I think this is theorem 1. I don't know the numbering. Okay, so that finishes that. So now we will go and I'll actually give you a so just one so back to typicality, and after that we'll go to types. So I mentioned this yesterday. So you have this big xn, right? And you are looking at the measure pxn, that is, this is the product measure. So how does it look? As n becomes large, so there is one set. So this is T delta N Px, and all the mass is getting concentrated on this. And furthermore, what is interesting is that it's becoming uniform on this set. If you observe, it's becoming completely uniform on this set, exponentially uniform. And outside it is, outside it has gone completely, it has become extremely weak. Okay, so all this has become extremely weak, and this will contribute. This will contribute at most epsilon. The size of this set is close to h of px. So I will just say e to the power n h of px. And each fellow here has mass exactly e to the power minus n h of px. So it's becoming uniform there, right? So we will see this become even more interesting as we go into two sets. Okay. So now I will do joint typicality. And you will see an even more interesting picture come across, and you will actually see what is covering, and I mean just a preview of what is covering and packing. Okay, so now I have two sets, X and Y. I have a joint PMF, PXY. So this is a joint PMF. So, you can think of X to be, let's say, binary. This is also Y. For example, you can take PXY. So I will just give you one example on the right so that you can have this in your mind. So this is X 1 0 1. Okay, so I take 1 minus delta by 2, 1 minus delta by 2. I think I should not. So I'll say eta. Okay. There's no reason to believe eta is small or anything, but I don't want that to be delta and epsilon because you might relate to the previous one. So eta is a constant. Okay, it's some number. It could be 1/4 or something sort. They all add to 1. So this is a distribution. Now what am I looking at? So I will define. So clearly we have, so I can consider xn, yn, right? Xn, yn belong to xn cross yn, right? So what is this? This is a collection of pairs. Just like you had one, you have now a collection of pairs. So this is your xn comma yn, right? And I can ask what is the number of occurrences of a particular AB, right? In this case, I could ask, how many 0 1s were there in the entire sequence you saw. Like one example would be something like this. So this is really what I mean by x8 y8. Okay, so I have 8 4 5 6 7 8. So x1 y1 is 0 1, this guy, and this is x6 y6. And you can ask the question, how many 0 1s did you see in the entire sequence? So this is one such 0 1, and this is another such 0 1, and this is another such 0 1. So there are 3. Okay. Yeah. Okay. So I will do kind of similar thing, and initially it's all very simple, but then as we go along, it gets interesting. So so given delta greater than 0, so T delta N PXY now have a joint type. It's called a jointly typical sequences. So it's the set of all those pairs of sequences where the relative frequency of every pair is close to the distribution that you chose. So there is really nothing new in this definition. You could have just taken your big X as big X as X cross Y, and everything is consistent. There's no problem. Okay. Nothing special at all. So clearly I will state three lemmas and standard from the previous thing. So exp. Okay. So I should also define what is joint entropy. So joint entropy is also defined. So define. So the joint entropy H of Pxy, many times I will just say xy, okay, is defined as standard, no change. You had one, now you have two with a minus sign. AB belonging to xy. Pxy of AB log Pxy of AB. Okay. So everything, 1, 2, 3 go through as is. I'm not going to, it'll be very crisp. So Pxy, so I will say this 1 by n log Pxy of a comma b minus, so this is close to, so this is h of xy plus or minus delta. Okay, I'm just writing the exponent straight. I'm kind of writing down plus or minus. Okay.
So I'm going.
Yeah.
What exactly is n?
What exactly
b
is?
Of what is n a comma b of x and y?
Same thing. So n of a comma b, I think I did this right. I did it here. So n of a comma b given x and yn is the I equal to 1 through n indicator function, your xi equal to a and your yi equal to b.
Ah.
So if you
Yeah.
see this, so the number of 0 ones, so I will do this. So the number of 0 ones, that's my AB.
Yeah.
In the sequence x8, y8 is I count this is 1, this is 2, and this is 3. So that's why I have 3. Okay.
So it's really the exact thing on the joint distribution of.
Yeah, exactly. There is absolutely no
these.
change. Why? Yeah, absolutely no change. So you can do all of the previous thing. You can just take z plus x tensor, x cross y, and everything goes through. The same definition will come. You're just now treating your alphabet as x cross y. Is that okay?
Yeah.
Okay, great. So I have this, no change at all. The first is as is. Second, so if I look at this, for any epsilon greater than 0, there exists an n epsilon delta large enough such that for all n larger than n epsilon delta, if I go long enough in my observation, then the probability that I will end up in that typical set, so xn yn belongs to t delta n pxy, the probability that I will end up landing there, that is this. The probability that I'll end up landing there is this. Okay. That is pxy n of xn yn. So this is greater than or equal to 1 minus epsilon, sufficiently large. 3, if I look at 1 by n, the rate at which this set is growing, this is h of xy plus or minus. I'll just put a 2 delta here because remember that day we had an epsilon thing. You will actually see this. You will actually prove all this. This is not the important thing, but there will be one more statement. But you will all prove all this in the homework. I'm going to post the homework right today. Okay, this is standard stuff. Nothing is there to be done here. But I will go further. Now, when you have a joint distribution, so now I'll come to conditional types. and it gets super interesting here. Conditional typicality and conditional entropy. We will come to this and you will see, you will actually see packing and covering. Okay, so if I have a distribution, I can talk of Px given y, right? Px given y, x given y. What is this? So suppose I observe y. So what is this? This is a distribution. It's a distribution Px dot given y. That dot runs over x, right? So for example, you could take Px given y of 0 given 1, comma Px given y of 1 given 0, 1 given 1. So I fixed my y to be 1, like in this case. I fixed my y to be 1. I fixed my y to be 1. So I am looking at this distribution, but I will divide by py of y. So I'll divide by half. So Px given y of 0 given 1 is eta by 2 divided by 1 by 2. This is py of y. This denominator is py of 1. And Px given y of 1 given 1 is 1 minus eta. Whole by 2, whole by 2. So I get 1 minus eta. Okay. So this is eta. This is eta. This is 1 minus eta. Okay. So I have a distribution. That is my conditional distribution. So what I do, so I have a conditional distribution. So I'll just mention remark. I mean, this is, I don't need to do all this. I'm assuming a lot of this, but just to, wake everybody of you up if you're not yet awake. So this is a PMF on X. So I get a family of PMFs on X, right? Okay, so definition. Okay, suppose yn belongs to yn, some sequence, given delta is greater than 0, the conditional typical set of X given the sequence yn. Okay, given yn. So this is the definition. Okay, so is a conditional typical set denoted T delta n P x y given yn is, I will progressively get lazy, and I'll tell you what will I write when I get progressively lazy, but just hold on. So this is the set of all those xn's such that if you couple them with the yn that is sitting here, this is jointly typical. Remember, I only have joint typicality, so I don't have anything else. So I take all those. So somebody has given me a yn. I take all those kind of xn's. I'm going to take all those xn's in that thing. When I append it with the yn, it becomes typical. It becomes jointly typical with respect to pxy. Okay. That's why you have the pxy sitting here. Okay.
So
I
is
know.
this,
Sorry. Go ahead.
okay, is this the typical set on that disk? Is this equivalent to the typical set on that distribution itself?
Not able to hear anything, firstly, but I suggest you hold on, because this will not be very clear to you right now, but just hold on. So just hold on. This is, kind of have this mental picture and keep going. You can repeat your question once again. If your network is slightly better, I'll listen to it. But my guess is,
Hello.
yeah, go ahead. Now go ahead. Hello, go ahead. Okay. Can you hear me? Can somebody else hear me?
Yeah,
Yes.
yeah, we can hear.
Okay. So for the moment, you might not get complete intuition what this
Okay.
is. Go ahead and ask your question quickly, and then I will pause and answer it. Who was the one who began to ask something, but I couldn't hear? Okay. Possibly one of you has dropped out. Okay, I will keep going. So I will just keep going, and then question. I mean, when the question becomes clear, I'll answer it. So okay, I will make a couple more definitions. So there is a distribution out here, right? There is a distribution. So recall. So recall. I'll also make a couple more definitions, and then I'll connect all of them. So recall, given pxy, a PMF on x cross y, we have a family of distributions of PMFs on x. That family is this. So look, fix one y, you have a distribution on x, and for each y you can take one, and you will get a family of distributions, right? Each one is a family. I mean, each one is a distribution. So so definition. So when I have a distribution, I can define an entropy, right? So suppose Pxy is a PMF on x cross y. Okay. The conditional entropy of x given y equal to y is defined as h of, I mean, most likely I will write it like this, but I will also possibly sometimes write it like this. So this is just the entropy of the distribution. So y is fixed. So I'm going to sum over x belonging to x, px given y of x given y log px given y of x given y. Okay. So this is given. Okay. So this is conditional entropy of x given y. Okay. I'm going to now define. So this is for a fixed y. For every y, I have these guys. So I'm going to average it now. So the conditional entropy of x given capital Y, no realization, okay, is defined as h of x given y. So there is no equal to there. These these guys are not here anymore. So I have to average it. So what I do is I'll average it with the distribution y. So I'll kind of give you some feel for what's going on. H of x given y equal to y. So you just average it with the distribution y. Okay. So think of so what's kind of going on.
So what's the difference between the two things? Like, both the things are conditional entropy of x given y.
Yeah, but see here the distributions are different, right? So I mean, just for a simple case, I'm not sure why you get this question. So let me do this. So let me do a simple setting. So 0, 1. Okay. So 0, 1, 0, 1. A, B, C, 1 minus A minus B minus C. This is a distribution, joint distribution. So what is P x given y equal to 1? So what is this given y equal to 1? So this is B given 1 minus A minus C. So look at this. This is, so at the bottom I will write the marginals. You know what is a marginal, right? So this is 1 minus, so this is the probability. So this is the, okay, so 1 minus A minus C. So this is the probability of y equal to 1. What is the probability of y equal to 0? It is A plus C, probability of y equal to 0. This is the probability of y equal to x, that is A plus B. And this is 1 minus A minus B. Okay, so this is probability that x equal to 0. This is probability that x equal to 1. Okay, so now let's look at look at this distribution. X given y equal x equal to 0 given y equal to 1, and x equal to 0 given y equal to x equal to x given y 1 given 1. Let's look at this. What is this? This is 1 minus A minus B minus C divided by 1 minus A minus C. Okay, this is the conditional. So when I look at h of x given y equal to 1, I'm looking at the entropy of this distribution. Okay, let's look at what is the other distribution, x given y equal to 0 given 0. Okay, what is this? This is A by A plus C. And x given y 1 given 0, x given y 1 given 0 is C by A plus C. So observe that these two distributions are different. Okay, so h of x given y equal to 1 is going to be different from h of x given y equal to 0. So these two are two different entropies. Now, if I average them, I get this entropy. Average them with what distribution? With the y equal to 0, y equal to 1 distribution. So I look at this entropy and multiply it with, so h of x given y equal to 1, multiply it with the probability of y equal to 1. What is the probability of y equal to 1? It is 1 minus A minus C. Okay. Plus h of x given y equal to 0, I multiply it with probability of y equal to 0. What is this? This is A plus C. So when I do this, this is my h of x given y. So this object is different, this object is different, this object is different. Does that make sense?
Yes.
Hello?
Yes, sir.
Okay. Any other questions?
Yeah, so you
Yeah.
you defined the typical set for the conditional distribution.
Yeah.
That is not just the same as
No. I have not. No. You have to be careful.
uh,
I have not. I have not taken the conditional distribution.
I mean, right.
Sorry.
Right. Yeah, so my question is this the same as the typical set of the conditional distribution?
We will come to that. We will come to that. We will come to that. It's not clear what you
Okay.
defined. So we'll come to that. We'll come to that. So we will first, we will come to that. That's a consequence. It's not, I'm giving you, after some work, make it slightly simplify, and that may be slightly hard to think about. So this is slightly easier to think about. See what is going on here. Okay, so let me go ahead. So now we have defined h of x given y equal to 0. We have defined, h of y equal to y for every y we have defined. We have also defined h of x given y. Okay? That's all we have defined so far. So now I will make some statements, and now you will see certain things come. All of this you will prove yourself. Okay, but we will now get to some intuition. Actually, before I prove, let me make some statements, and then we will prove the statement. So, so simple properties of entropy. So joint, conditional, everything. Okay, I will just so on the right, I will just write the definition so that you kind of have it the back of your mind. H of pxy given y equal to y. So this is x, y, both will sum. Here I have only x summing. Px given y, x given y, log p x given y, x given y. And then h of x given y. This is this is an average of the entropies. Okay, this is an average of the entropies averaged with the distribution y. Okay, so so I'll maybe give some intuition before I prove I make the theorem statements. See, remember yesterday we were doing, yesterday and before yesterday we were doing this. So we are observing some source x distributed according to px, right? And the question is, how many bits should I put on a wire so that this guy will reconstruct whatever xn I see here? This guy has to be able to reconstruct that, right? How many bits I have to send? I have to send h of px number of bits. This is what we did, right? Now what is happening? Think of the following. So suppose each fellow is observing yn sequence. Okay, so yn is kind of something common that both of them are seeing. So you always think of this as Alice and this is Bob. Okay, so Alice and Bob are observing yn. Both of them are observing yn, the same yn. Okay, so I will just put a link here, the same yn. But in addition, Alice is observing xn, and that xn has to go to this. Okay, so Bob is not observing xn, but Bob is observing yn, and that xn has to go. Okay, it turns out what we will need is the conditional entropy of x given y. Okay, that's why this has some physical significance. But something even interesting will happen as we go along. But just get so this is the h of px is like the uncertainty. As I told you, it's like the uncertainty in the source. On an average, the uncertainty is h of px. It's not log cardinality of x. Okay, it is h of px. So when somebody is observing yn, what is the uncertainty in xn, which is related to yn? That turns out to be h of x given y. Okay, I will make some statements and then kind of show what's going on. So lemma, some simple things, okay, which you will show in your homework, but I will for now assume you can kind of see this. These are not difficult. So the entropy is always positive. Any entropy is always positive, and it is upper bounded by the log of the cardinality of the set on which it lives. So uncertainty can't be greater than log cardinality of x, right? That's the worst you can get. 2. So suppose I have a joint distribution pxy, right? Then I can obtain marginals, right? I can obtain marginals px and py. So what is the distribution on x? What is the distribution on y, right? So I can ask, so this distribution on x has some uncertainty, x. This distribution has some uncertainty, h of y, right? And I can ask the question, how is the joint entropy related to the individual entropy? So this is the uncertainty if somebody is only looking at trying to predict x. This is the uncertainty if somebody is only trying to predict y. This is the uncertainty if somebody is trying to predict both x and y. Okay. So it turns out that if you know x, right? So if you know x, your uncertainty in y is lesser. Like go for that example. So recall that simple example 0 1 0 1. Okay, so this is x and this is y. Okay, so let's take that simple example 1 minus eta by 2, 1 minus eta by 2, eta by 2, and eta by 2. Okay, so suppose eta is say 1 by 8. Right. So what are these terms? I'm going to write these terms down in red. So it's 1 minus 1 by 8 is 7 by 8. 7 by 8 is 7 by 16. Maybe I should, yeah, okay. So this is 1 by 16. This is 7 by 16. And this is 1 by 16. So if I tell you, if I don't tell you anything about, if I look at the distribution of x, the distribution of x is 1 by 2 if you observe. 1 by 2, 1 by 2. The distribution of y is 1 by 2, 1 by 2. You can check this out. Okay. So the marginals are equally likely. Okay. Now, if I tell you that I observed y is 1, right, the probability that you will observe x is 1. So if you look at this, probability that x given y, 0 given 1, is actually going to be 1 by 8. And the probability that x given y, 1 given 1, is 7 by 8. You can check this. So if I tell you, so before I told you nothing, I did not tell you anything about y. If you have to predict x, you have no way to predict. You just toss a coin and predict, right? The coin is equally likely. But if I tell you that y is 1, then your uncertainty in x is much lesser because you're looking at the entropy of this. The entropy of this is much lesser. Okay. So, so that means that, so the joint entropy is the uncertainty in x. Once x is revealed, y. So uncertainty in y. So once y is revealed, the excess entropy that you need to reveal x also next is smaller, right? So the intuition suggests that, so if you observe here, right, if I look at the joint entropy, okay, so I'll make a simple thing. So if I look at the uncertainty in x, you will get 1. Okay, you can calculate it. I mean, this is just the entropy of this. Everything is to the base 2. Okay. If I look at the joint entropy of y, I will get 1. Okay. But if I look at the entropy of x, y, you will not get 2. You will get 1 plus something much smaller than 1. This is going to be the entropy of this guy. And that's going to be much lesser. I mean, you can do the calculation and show. So the individual entropies sum to a number larger than the joint entropy. That's your second property. I will, I'm doing all this because I'm not giving a proof, and you will give the proof in the homework. So the entropy of px plus the entropy of py is in general strictly larger than the entropy of xy. So this is called subadditivity. So you just use, do some little bit of math and you will be able to show this. Okay, and the third thing you can show is the, so recall how we defined conditional entropy. Conditional entropy was defined like this. So first you define this, right? So this is, so I will just write the entropy of the vector px given y, something given y. So I'll write this. So x is, y is fixed, and you're looking at the entropy of the vector of this vector. That's your this thing. And h of x given y is py of y, h of x given y equal to y. This is how it was defined. You will show that h of x entropy of x, plus h of y given x is h of xy. So that is the unconditional entropy plus the conditional entropy is the joint entropy. And just algebra, literally algebra. This will require a little bit of small inequality, but otherwise, again, it's this is again a little bit of inequality. But whatever you use in one, you will also use in two in some sense. I'm just proving certain simple properties. I'm not proving. I'm just stating some simple properties which will come to which will get us somewhere. Okay, so now I will so I've kind of introduced a bunch of loaded you with a bunch of terms. So one is I defined what is called the conditional entropy, just the conditional entropy. Then before that I defined what is the conditional typical set. This is a little different thing. So given yn, I'm looking at all those xn's that are jointly typical with my yn. Okay, so if I look at the xn's, I know there are a bunch of x and yns that are typical, but now I fix a yn and I look at all those guys that are jointly typical. So let me start to write some pictures and then it'll become clear. So this is my T delta n pxy. Okay, so all jointly typical pairs. So it's actually a two-dimensional set, but I'm not going to complicate it. So take a guy here. There's going to be an xn and there's going to be a yn. Take another guy here. There's going to be an x tilde n and a y tilde n. Take another guy here. There's going to be an x hat n and a y hat n. We'll take one more guy here. Possibly the y is the same. Some y has matched. So look at all these guys with the same second coordinate. This will fall in the T delta n pxy given y tilde n. Right? So all these guys, not these guys, but essentially the x parts of them will fall inside this. So this guy will have your x bar n and an x tilde n and so on. That's what. So I'm looking at cuts of this joint typical set. That's what is the conditional typical set for every y, right? And you may ask this question. Suppose I take a yn. Will I always lead to something T delta n pxy given yn? May not be, right? If that yn, you don't see that yn at all, you will not see it. So it will be an empty set. It could be an empty. Can be. Okay, because if it doesn't have any, it doesn't get married to any xn to be jointly typical, it's bad. But for every pair, you can fish out the one of the index and then look at the jointly typical, conditional typical set of the other guy, right? So what I can do this, right? I can push these guys around. So I can just kind of push this guy closer to this, and all the red guys, right? I can push all the red guys wherever they are. So they have the same second coordinate, and there are some different second coordinates somewhere here, right? I can push all of them, right? And I can get a new a new picture, right? So what is the new picture? The new pictures look something like this. So there will be orange guys, right? There will be but see, there's one thing that you have to, okay, so let me write this down, and then the red guys, there's a blue guys, there are purple guys, right? But these pictures are non-intersecting, but the xn's may be common. Okay, so in other words, so these are all the yn guys. Okay, these are all the y tilde n guys. These are all the y bar n guys. Okay, these are all the y hat n guys. Okay, but the xn here might be here also. The pair is different, but the xn's may be the same. So the xn might be here also. Some sets it won't be there. So it's a very involved set. Like the sets don't intersect, but the xn's might be the same. Okay, so this is xn y hat n, right? This is xn y tilde n. They are distinct pairs, but the conditional typical sets are intersecting, right? The conditional typical sets are intersecting. So T delta n pxy of y hat n, this intersection T delta n pxy of y tilde n, these are intersecting. Okay, because remember, these are only those xn's that get married with the y hat n. So xn comma y hat n is jointly typical. So the xn's might match, but the pairs are different. So I can do this kind of shifting around. Is this okay? Now, I will do a slightly different picture. Slightly different picture. I'll do a slightly different picture. So now what I do, I take the xn only, T delta n. So I take the xn's only. Okay, so maybe I should mention one small point before I go ahead. So this is maybe interesting, not a big deal. So I told you, right? So remember, what all have we started with? We've started with an x, we have a y, we have a joint distribution pxy, right? You can see, as you know, with just two letters how things are slowly getting more complicated, right? It turns out it's always like that. Even with two sets, even with just two, things get slowly, get complicated. So anyway, so what do? I fix a yn, right? I fix a yn, and I ask this question, give me all those guys that when I link it with the yn, I am falling inside this nice set, right? So all those xn's such that when I pair it with the yn, it turns out to be a nice pair, right? This is my jointly typical set. And I also told you, you don't know. I mean, sometimes a yn might not be paired at all, right? Sometimes a yn might not be paired at all. I mean, it may not have any xn. I mean, it has to live alone. So can we say something? Yes, we can. If xn yn is typical, okay, so if xn yn is typical, so if the pair is typical, then if I take them individually, they are individually typical. So that means xn is in the individual typical set. It can't be like, it can't be an outlier by itself. I will actually explain what this means. And similarly, the yn also has to be typical according to its own guy. Okay. So let me explain this. So I will explain this with that example. So recall that example. I took 1 by this guy, 7 by 16, 1 by 16. So 7 by 16, 1 by 16, 7 by 16, 1 by 16, right? This is your example. So 0, 1, 0, 1. So when I say x, so suppose, these are all binary. So essentially I have xn, yn is some pair of binary. So I'll write it like this, it looks something like this. I'm just randomly writing something. Okay. Now, this pair is going to be jointly typical if the fraction of 0 zeros is close to 16, right? 0, 0, close to. The fraction of 0 ones, so this is x, this is y, is close to 1 by 16. The fraction of 1 zeros is close to 1 by 60, and the fraction of ones is close to 7 by 60. So you count, how many zeros are there, how many ones are there. If it is close, within that epsilon guy, it is true. Okay. So what I'm saying is, if I take such a pair and I look at the frequency of zeros in this guy, that will be close to 1 by 2, because the x distributions are 1 by 2, 1 by 2, 1 by 2, 1 by 2. That's the y distribution. So when I'm writing this thing, I'm adding these two guys. And I'm adding these two guys. Okay.
But the delta might.
No. The delta also will not. So I will tell you. So when I write this number, what am I doing? I'm adding these two guys. When I write this number, I'm adding these two guys. Okay. When I write this number, I'm adding these two guys. Why am I doing that? Because px of 1 is pxy of 1 0 plus pxy of 1 1. I'm doing all this because I'm assuming that you guys don't play with probability like I do. So I'm adding these two guys. This is the marginal of y. This is the marginal of x. Okay. So what I'm saying is that suppose I take a pair that is faithful to this joint distribution. It's faithful to this joint distribution. Then if I forget the yn, then that xn sequence is faithful to this distribution. And that yn is faithful to this distribution. Okay. So that's what I'm saying here. So if the pair is faithful to the joint distribution, individually they are faithful to their own distributions. It's not difficult to see because you'll actually prove this. So one of you said, is it the different delta? No, it is exactly the same delta. You can show it. It's actually trivial. So it's exactly joint. It's exactly this. So that means if I take a so that tells you something, right? What does it tell you? Now, so it tells me something. Remember, what is this? Pxy given yn. This is the conditional typical set. So I'm asking you, give me all those xn guys, such that if I pair it with the yn, it is jointly typical according to T delta n. I mean, jointly typical according to Pxy. Now, if my yn was not even in the individual typical, it did not behave well individually, how can you marry it with somebody? Because if there was somebody here, then you know that the xn yn was jointly typical. But then that from my previous statement implies that the yn was typical according to itself, but we know it is not, right? So that means if I look at each, so if I go back to this picture and I fish out all those yn guys, they will all be inside the individual typical set. Similarly, if I fish out all the xn guys, they will be in that. They can't individually behave badly. Okay. I've told a lot, so I'm going to just pause. Only 3 minutes. I'll just pause. Questions, thoughts, ideas, let me know. I was hoping that I will give you some idea of covering and packing. I don't have enough time and I don't want to do it, but I will do it in the next class. So just to maybe briefly give you an idea of packing and covering, what I will do is, so this is the typical set, and what we will do is we will partition it. We will cover it with disjoint pieces. That's kind of covering and packing. You'll see that come across. So I will break this big setup into tiles, and I will cover the entire space, or I will pack the entire space. So that's kind of covering at a broad idea, but I will just pause for questions and thoughts. Questions, and I'm sure that some of you would be slightly feeling things are new. No questions? Either everything is clear or everything is clear. everything is absolutely clear, you got nothing, or everything is clear, you got everything.
Yeah, I think it's fine.
Okay. So maybe I will just give a small preview of what's going on. Sorry?
I have a question. So,
Yeah.
how does this joint entropy relate to the usual notion of amount of surprise uh, in the distribution?
So the joint entropy is the amount of surprise in you're observing the pair.
Okay.
So that amount of surprise. So if you see, there's one equal. So I will write this. So I'll explain this. So look at this. So I'll kind of explain what that is. So the amount of surprise in the pair can be divided into two disjoint surprises. The first surprise is in your X. Now, having told X, you have some surprise in Y, and that is the conditional entropy. So the conditional entropy is the surprise of Y given that you know X. So look at that distribution again: 7 by 16, 1 by 16, 1 by 16, 7 by 16. So so first, so that's what the marginals are 1 by 2, 1 by 2. So initially you don't know anything, and when I reveal X to you, I eliminate one bit of surprise in you. Now, having observed X, you have a fairly good sense of what Y is. So your amount of surprise in Y reduces. That is why when suppose I tell you X is 1, then you're not too surprised if I tell you Y is 1 after that, right? So the second level of surprise is this, which is smaller than 1 bit. So this object is going to be smaller than 1 bit. You will see that this is entropy of, this is 1 by 8 log 8 plus 7 by 8 log 8 by 7. I'm just writing the entropy, conditional entropy. So you observe what this will be. This will be log 8 minus 7 by 8 log 7, which is much less than 1. So that is, but on the other hand, h of x plus h of y is greater than, that means individually, I mean, if I don't tell, this is if I don't tell you anything, this is if I don't tell you anything, the surprise in x. This is unrelated surprise, this is some other y. So this surprise is more than the joint surprise. That's what subadditivity is telling. Is that okay?
Okay. Thank you.
No, but if you have any follow-up, like something tangling, let me know, because it could help the others too.
Okay, it's fine. Yeah.
Okay.
Yeah.
Okay, cool. So I will end now. I will post a homework. I will I don't actually how I post a homework. So so do one thing. All those guys who plan to register, send me an email right today. So send an email to you can just send an email to this. And I will send you the homework right today or at most tomorrow, and it'll be due next week, because I only wanted to do next week, not because generally I don't want to make it due only 1 week, but I want to make it due next week only because the material will build upon. So if you don't solve this, you will be slightly finding the next part. I want you to be kind of ready for it. Next week, actually, I'll be doing covering and packing. You have everything to be able to do covering and packing, and this inequality is actually telling you covering and packing. What it is saying is that this jointly typical set can be partitioned into so many number of conditional typical sets. That's your covering packing kind of a statement. But all of that makes sense only if if you solve all these exercises, then you can connect the dots. Okay, I'll end the class.